Welcome you are today video lecture. We will start discussing orthogonal random variables. So we are continuing our topic based on um, pair of random variables. So the first definition today is orthogonal random variable. So if you have a random variable x and y, they are orthogonal if and only if their correlation is 0. Now the next important analysis point is uncorrelated random variables. If you have a random variables x and y, they are uncorrelated if their covariance is 0. So these all matrices are used for analysis purpose when we have two pair of random variables. Now as you know that we have this theorem, and its theorem is that if you have independent random variables, so this is the benefit when we have two independent random variables, for example say x and y. So in that case, the first one is if we take the expected value of function of random variable x times the function of random variable y is equal to their uh, multiplication of their expected values. Okay, so if I take the product of function and take the expected value is equal to their product expected values. So the second thing is correlation. So correlation, if you remember, is equal to expected value of x and y if it is uh, independent. So uh, this correlation can be equal to product of their expected values. And covariance, as we know that if they are independent, so covariance and correlation coefficient is 0. Similarly, if we take the variance of x plus y is also equal to variance of x plus variance of y. So these are the properties only satisfy when you have two random variable x and y and they must be independent. Now this is the theorem, proof for that theorem which we discussed. Now assume we have an example, and this is uh, we use a lot in practical scenario. So for example, if you have a noisy observation, normally in communication system and networks we observe something or receive something. So for example, your observation is y, and it has as your information x and noise z. Okay, so we extend this example from our previous example that we discussed, and now find the covariance of x and z and covariance of x and y and the correlation coefficient with respect to x and z and x and y. Now as we know that um, if we go to the previous example from where we get the data, we know that the signal x is a Gaussian one with mean value 0 and standard deviation rho of sigma of x, and the z is the noise, and this is also Gaussian with mean 0 and standard deviation sigma z, and x and z are independent. That this is the information we have from the previous example. So if we apply the theorem, we know that covariance of xz is equal to 0. Similarly, variance of y is equal to variance of x plus variance of z. So that is equal to square of standard deviation of x plus square of standard deviation of z. Similarly, as we know that expected value, because it is given to us that expected value of x is 0, expected value of z is 0. So this means that expected value of x is equal to expected value of z, and this is also equal to 0. Now expected value of y is actually equal to expected value of x plus expected value of 0. As we know that this is 0, so expected value of y is also 0. Now as from the theorem, as x and z are independent, so this means that expected value of product of x and z is equal to uh, product of their expected value. So in that case is also 0. Now we want to calculate the covariance of x and y. Now we are set here, we can do it. So this is equal to expected value of x and y, and we already know that expected value of mm, x can be written as x times, instead of y, we know the formula from the previous slide that y is equal to x plus z. So just we plug in here x plus z and we solve it. This becomes x square plus x times z. Now we have to take the expected value of this, as we know that these are independent, so this can be written as expected value of x square plus expected value of xz. So we already calculated that expected value of xz is 0, so this becomes expected value of x square, and we know that expected value of x square is sigma square. So this implies that we know we calculate the covariance of x and y. So similarly we can calculate the correlation coefficient. So in that case, rho is equal to x comma y, the covariance divided by under root of variance of x times variance of y. Just plug in the values, we calculate this formula. So this is the way, and this is the benefit of independent random variables. So based on independent random variables, we already calculate the correlation coefficient without knowing all the information. So independence is very important. So that's why in communication system we want to signal to be independent to each other so that we can extract the information. Now this is a quiz here, and quiz says that if we have a random variables, say L and T, but have a joint PMF given to us. Now these random variables actually are discrete in nature, and this is that the PMF they are different paging and timing. Okay, so if we have a one page, so time is 0.15. Sorry, probability is 1.15 when time is 40 seconds. Similarly, when time is 60 seconds, probability is zero point 0.1. Similarly, so this is a joint PMF given to us with respect to L and T. Now question is find the following quantities. So first one is expected value of L, second is variance of L, then we have to find the expected value of T and variance of T, then the covariance L comma T and the correlation coefficient. Now the first thing for this one, we have to calculate the partial PMF for L and T so that we can apply the formula of for expected values and variances. Now let's see the solution on the next slide. So here what we did here, we calculate the expected value of L. How we do that? So we calculate first the partial PMF with respect to L, similarly partial PMF with respect to T. So from here we know that partial PMF uh, becomes 1 into 0.25 plus 2 into 0.25 plus 3 into 0.25. So this will give us expected value of L. Similarly square and then apply the formula for variance. So we easily calculate the variance. Now in case of T we do the same thing. First we have to calculate the partial uh, PMF and then we can apply the formula. Now after that we just plug in the formula for T, we calculate the variance. Now then question is to find the expected value of L and T. So we have to multiply L times T because we have two variation with respect to T and L. So we need two summation to solve it. Now from here we calculate expected value of LT is 96. Now covariance, if you remember, the formula was that expected value of LT minus expected value of L times expected value of T. We just plug in the values and we get this becomes 0. So if covariance is 0, so this means that T and L are independent. So similarly, covariance is 0, the correlation is also 0. Now the second part of quiz is for continuous random variables. Now we have two continuous random variables, say x and y. Now joint probability density function is given to us in terms of x and y, and with this definition and he asks you to calculate expected value of x, variance and covariance and correlation coefficient. So first thing is to calculate the partial probability density function. So for that reason, you have to take the limits from minus infinity to infinity with the joint PMF, and for x do it for y, and you calculate it becomes 2x. Similarly for y it becomes y by 2. Now after that you are set to calculate the expected value. So for expected value we have to multiply x times the partial density function and do the integration from minus infinity to infinity. It becomes 2 by 3. Similarly x squared becomes 1 by 2. Now when you do that, you can easily calculate the variance, because the formula for variance is expected value x square minus expected square of expected value. So this is the way you can calculate the variance. Now similarly you can do for y. Now after that you have to calculate the covariance of x and y. For that you need to expected value of x and y. So in that case you need double integral and it becomes 8 by 9, and just plug in the values, it becomes 0. So as x and y covariance is 0, so correlation coefficient is also 0 due to the formula. So this means that x and y are independent. Now the last topic is the bivariant Gaussian random variable. So if you remember, we have a Gaussian random variable. Now here we are based on two random variables, pair of random. So in that case it is known as bivariant Gaussian random variable. So it has um, PDF parameters, that is mean of x, mean of y, standard deviation of x and y, and then the correlation coefficient. So this is the formula we get when we have two uh, pair of random variables for Gaussian random. Is also known as bivariate Gaussian random variable. Now this is the formation. If we plot it with respect to x and y in 3D plot, you see that if the relation between x and y, they have different uh, what you say picture for in 3D. For example, if reciprocal relation, or in other words if rho is in negative side, correlation coefficient, so in that case you have this type of spectral relation between x and y. So this is the 3D plot you get between x and y, and this is the probability density function, joint probability density function of x and y. Similarly, if it is scattered, so it means that if your correlation coefficient is 0, so there is no well-defined relation between x and y. So in that case, you have this type of result, which is in 3D plot. Similarly, if you have a linear relation between them, so on, in other words, your correlation coefficient is from 0 to 1. So in that case, you have this relation that going in this direction. So this is the behavior you get based on the relation between x and y for bivariant Gaussian random variables. Now similarly for partial, as we know that this is the same definition for partial x and y for Gaussian case. So now the theorem is that if you have a bivariant Gaussian random variable x and y, so we have correlation coefficient between x and y is represented by rho x comma y. So bivariant random variable x and y are uncorrelated if and only if they are independent. So for example, if we have two random variables, that is x and y, and they are bivariant Gaussian, PDF given as we know that with respect to x and y. Assume that we have W and W2 are linear independent equations, that is W1 is equal to A1x plus B1y. Similarly, W2 is A2x. So if I take the expected value of any W, it becomes AI times the mean plus BI times mean of this. Similarly for variances, this is the relation. This is the whole same for W1, W2. Now if I take the covariance between them, so in that case covariance, this is the result you get for covariance. So if we have bivariant Gaussian random variable with linear independent equation, so this is the relation we get in terms of expected value variance and covariance. Now example, for the noisy observation, same one, we have y is equal to x plus z. Now if I have to write the, we know that this is a Gaussian with respect to expected value 0 and standard deviation a sigma of x. So in that case, we know that expected value of y is 0 and covariance is x square plus z square. So in that case, the PDF of y is written as this one. Now, if we continue the same example, and in this example, if we assume that the standard deviation is 4 and standard deviation of z is 3, so in that case, we easily calculate the correlation coefficient using this formula, that becomes 4 by 5. So in that case, now our joint PDF bivariant Gaussian random variable can be written in this form. Now the last quiz, and then we stop here. And quiz says that, for example, if you have two random variables, assume you have x and y, they are jointly Gaussian with 0, 1, and random variable with correlation coefficient given to is 1 by 2. What is the joint PDF of x and y? So we just write the information that we know, that we also know that rho is 1 by 2. Now we apply the definition and we just plug in the values. This is the result we are getting. So now we will look at multivariant modes, probability modes. So in that case, if we have more than one random variable, so assume that you have x1 to xn, so in that case the CDF is given to us as the same definition extended from 2 to n pair of random variables. So similarly, PMF is also extended to n random. Now same thing as we did for two random variables, here we have a multiple random variables. So to calculate the joint PDF, so we have to take the that number of partial derivatives to the CDF so that we can calculate the joint PDF. Now there's another theorem, and theorem says that this is also extension to the pair to the end, that PMF is either 0 or greater than 0. And similarly, if we add up all, it becomes 1. Now same thing goes to this theorem. We extended again that joint PDF is also equal to 0, is non-negative. And similarly, if you calculate the CDF from the joint PDF, you need the integration. So it depends upon the number of random variables. If there are n random variables, you need n integration. So similarly, if you integrate your joint probability density function from minus infinity, is become 1. So these are all extended definitions from pair of random variables to n pair of random variables. Now in case of discrete, if you want to find a probability, you have to, for an event, you have to look for the event variation in those um, random variables and just take the sum of PMF. Similarly, for continuous, you need that area where event is defined on based on n random variables and do the integration. Now this is an example. So, okay, you can solve this by yourself. Similarly, in case of this is very important theorem. So if you remember, we discussed the partial PMF. So here, because we have more than one pair of random variables, for example, to make things easier, assume that we have four pair of random variables w, x, y, z of discrete. So this is the PMF, joint PMF based on w, x, y, and z. If we want to do some marginal PMF, for example, if we want to find the marginal PMF with respect to x, y, z, so we have to take the summation with respect to w. If we want to calculate for wz, then we have to take the summation with respect to x and y for joint PMF. So means that we can find any pair of marginal PMF. Similarly, in case of continuous, we have to do the integration here. So if you want to calculate for, if we have joint probability density function with respect to w, x, y, z, and we want to do it for z, so in that case, for w, x, y, we have to take for z from minus infinity to infinity dz. If we want for x, we have to calculate, take the integration with respect to w, y, and z. Look here, we take the w, y, and z integration of joint probability density function. So the main idea is that here we have a pair of marginal periods. So we can find number of pairs based on what we want, and we just plug in the formula for that and do the integration. Now this is the example to clarify it. So example says that if you have four random variables y1 to y4 and it is defined here, this is your joint PDF given to you. Now question is to find the marginal pair with 1 and 4, 2 and 3 and 3. So for 1 and 4 you have to take the integration of 4 with respect to y2 and y3. For 2 and 3 you have to take the integration with respect to y1 and y4. For 3 you have to take the integration with respect to 1, 2 and 4. Now let's see the solution on next slide. Look here, 1 and 4 I take the integration with respect to 2 and 3 and solve it. Similarly um, for 2 and 3 I take with respect to 4 and 1. Now lastly for 3 I take with respect to all except 3 and we get this result. So if we have an independent random variable, so how we can look for independent? So independent random variable, so if you have a discrete one, your joint PMF is actually product of their marginal PMF. Similarly, in case of continuous, if you have a joint continuous PDF, joint PDF is actually product of their marginal PDFs. Now there's another term that is independent identical distributed. So independent means that we have independent, but there's another term is used, identical. So identical means that every marginal PDF has the same relation or same representation. So in that case, if you have a discrete, so joint PMF is actually product of marginal PMF. Similarly, joint PDF is also the same. But look here, we use x instead of x1 because these are all identical. They are the same, okay, representation. So that's why we use x here instead of x1, x2, x3. Okay. If you look at the previous, we use x1, x2, x3 because they are not identical. If they are identical, we use x because they have the same formulation or same representation, mathematical representation. Now assume to understand this, for example, if we have a random variables from x1 to xn and this is our joint PDF given to us. Now question is an event that denotes that maximum x is less than or equal to 1. Find probability of it. Now for this probability we have to look for all variables that satisfy this. So in that case we just do the integration and we get the result. So in that case probability of A is actually, if they are independent, so we just need to multiply their marginal PMF and we get the same result. Now the quiz to end this video lecture. And quiz says that if you have a 4 random variables and joint PDF is given to you, find the maximum. So this is the same, but this is for continuous one. So for continuous we need this integration uh, where this C is satisfied. So when we do that, we know that this is actually identical. 3 is identical. So we just use that, and when we solve this, it becomes 1 by 16. Now we will stop here. After this, we have a MATLAB representation, and we're not covering that in today's lecture. So this is what we did here. I just summarize. We start with pair of random variables, and we just extend to the multi random variables where we have more than one random variable. Okay, so we just see that we have the same representation. If you know the pair, you can do it for any number of pair of random variables. So thank you. I will stop here.